Hello, everyone, and welcome to my talk. My name is Guy Royse, and this is Dungeons, Dragons, and Graph Databases. I've taken a couple of my favorite things in the world, Dungeons and Dragons, and Graph Databases, and combined them together so that I can, have fun with them. So let's take a look here at what we got. As I get my desktop arranged. So I already introduced myself. I'm a developer advocate at Redis Labs. Redis Labs is, well, you've probably heard of Redis. Redis Labs are the people that make Redis. We fund the open source development of Redis. So go and check us out. I got some social links here as well. I'm going to try and go kind of fast here as well because I've got about 20 to 30 minutes, and this is originally a talk that was developed for about 45 minutes to 50 minutes. So if I go a little fast, don't worry, you can pause the video. So this is me. Now, normally I don't do this, but I thought I would also share my character sheet since this is a Dungeons and Dragons themed talk. And so here I have my name, and really the relevant details here are that I'm a dwarf, and I'm a level 5 dwarf, and that my charisma is high, but my intelligence and wisdom are low. So this talk should be all sizzle and no steak. But as a developer and a gamer, I've got a problem. As a dwarven adventurer, I've got this problem. I want to go through the dungeon. I want to go dungeon delving, and I want to find the best monsters to defeat so that I can get the experience and level up my character. And I want to find the rooms with the best gold so that I can cash that gold in and turn it into a better equipment so I can defeat more powerful monsters, get more XP, and go through that virtuous cycle of character advancement. And so that's my problem as a gamer. Now, since I'm also a developer, I thought, well, hey, I could solve this problem using a database. I could build an application and put in all the rooms, and I could put in all the monsters, and I can put all the treasure and do queries and figure out the best way to go through this dungeon to maximize the gold and to maximize the XP and to minimize the danger or whatever thing I want to do at that time. And so my first thought said I could use a relational database. I could take the rows and the columns and the joins and all that and make a big relational database. And to model that dungeon, I could query it. But then I thought I could also use a graph database. And graph databases are a little different from relational databases. They, instead of having the columns and the tables and the rows and everything, they've got nodes and edges that connect them together, or relationships and with properties and labels and all this great stuff. And so I thought I should do a talk on this. I should talk about what a graph database is by contrasting it with a relational database. So that's what we're going to do today. We're going to take a relational database, contrast it to a graph database, and hopefully you'll learn about graph databases. Now, I'm making an assumption in this talk, which is that you've used relational databases before and that you have a basic knowledge SQL. I have SQL in it. I'm going to talk about it a little bit, but I'm not going to go into detail on how that works. I'm going to talk about graph databases. I'm going to use it as a thing to contrast. Take something you know and then show how to do the same thing in something you possibly don't know. So, first question that I think needs to be answered is, what's a graph database? But to answer that question, we have to ask the next question under that, which is, what the heck's a graph? And a graph is, it's a set of nodes or vertices connected by relationships or edges. So this 20-sided die here, actually, I have a 20-sided die here. I've got a 20-sided die right here in my hands as well. This 20-sided die is a graph. It's got vertices, or points, or nodes. It's the points on our 20-sided die. And it has edges, which are the things that connect those vertices together. So you can't have a line without having 2 points. 2 points determine a line. So that edge is sort of that line. It's that relationship. And so this is a graph, and this graph represents a friendly, fun, 20-sided Platonic solid that we know and love, and that we roll all the time and hope we get a 20. But graphs don't have to be these things. The graph is the abstraction around this idea. The graph is the nodes and the relationships. It's the vertices and the edges. It doesn't have to do with geometry necessarily. It's just sort of its own thing. And so I'm going to go a little bit into how graphs work really quick, and then I'm going to talk about how graph databases, what they are specifically, and then we'll go into the mechanics actually making these things work. The simplest graph database is the Null graph. This is a graph that has no nodes and no relationships. Nothing to see here. Move along. The next layer here is we'll add some nodes here. And so now we've got a graph. This is a graph as well. It's got multiple nodes, but there's no relationships. They're just points floating in space. So we got just a collection of nodes. So let's relate them together a little bit. And so now we've got, might be considered a more proper graph here, where we've got nodes with relationships between them. So node D has a relationship to node A has a relationship to node C. But parts of this graph are not connected. For example, node E here doesn't have any relationships. It's isolated. But actually, nodes B and F, who do have a relationship to each other, that's also an isolated portion of this graph, or an isolated subgraph. And even the portion in the middle, which we might think of as sort of the main part of the graph, is isolated as well, because it's not connected to the complete graph. So when you have subgraphs that can't see each other, they have no paths to each other, they're isolated. Let's go ahead and connect all our nodes here so that our graph is no longer isolated. So there are no lonely nodes. And once we do that, we have a graph that is connected. So this graph is considered to be connected because every node has a path that can lead to another node. Every node doesn't connect every node, but every node has a path. So to get from D to F, we can go there by way of A and B, or by A, C, and B. And there's probably a few other paths there that we could tease out of there, maybe do some circles. But the point is that this graph is connected. Every node has some ultimate way of connecting to another node. You can also take a graph that's fully connected. And this is where every node is connected to every node in the graph. I've got here the subgraph here, the ABC here. They all connect to each other. And so that's a fully connected subgraph of this larger graph. You can create a graph that's completely fully connected, where every node is connected to every node. And you've seen those. These are the network star diagrams, where you've got actually a 5-pointed star with a pentagram inside of a pentagon is a fully connected graph. So that's a fully connected graph here. Something about this graph that I haven't really pointed out yet is that it's undirected, right? So these relationships, they don't have any direction to them. You can go from a node to a node. We know that A and B are related, but we don't know that there's any directionality to it. You can make directed graphs in my case, I just put little arrows on the lines. But a directed graph has extra data about it. Like if you think an A and B has a relationship that's directional, that means there's a little bit of extra data. So if you think of the example of like a mother and their child, there is a natural direction to that relationship. If the arrow pointed the other direction, that would mean something different, right? And so that's the kind of data that you can represent with a directed graph. Graphs have degrees, or more accurately, nodes within graphs have degrees. So a degree is the number of relationships heading in or out of a particular node. So node A has a degree of 3. And we can have out degrees, which is how many arrows point out, and we can have in degrees, which is how many arrows point in. And obviously, undirected graphs don't have in and out degrees because they don't have direction. But if you have direction, you can have in and out degrees as well. And you can pretty much connect anything to anything. There's not a lot of rules on how this works. You can have nodes that connect mutually to each other in a directed graph. You can have multiple connections to the same node in the same direction. That's perfectly valid. Nodes can connect to themselves. You can wire this up any way you want. All the stuff I've shown here is nice and neat and fits on a 2-dimensional sheet of paper, or virtual sheet of paper here. But they don't have to. I mean, this 20-sided die is, a graph as well, and it is taking up 3 dimensions. It's not really about the dimensions. It's about the nodes and the relationships. A graph database is when you take data and put it on top of the structure. So here we can take all the nodes and give them, labels, right? Some of these nodes can represent rooms in a dungeon. Some will represent the monsters, and some will represent the treasure. We can add data to those nodes. Here we've got a label of monster, and then we have some properties that we've added to that node. So Alice the elf, and down here we have Bob the ogre. Fun fact, Alice and Bob are my grandparents' names, and so it's fun that they're also sort of like the default users of any coding example you ever use. Although my grandfather was kind of elfin, but my grandfather was totally not an ogre. He was a wonderful old man. I miss him very much. But yeah, so we've laid data over top of these nodes. And we can put types on these relationships. And so now that these are leads to and contains relationships, showing that the room contains a monster, or this room leads to another room. And once we've laid all over that data over our graph, then we have ourselves a database worthy of Mordor, right? And this is in essence what a graph database is. To sort of sum that all up, we've got nodes and relationships in our graph database. The nodes tend to represent nouns. They are items. They have labels. They can have multiple labels. So a room could also have a node could have a label of room. Could also have a label of, say, chamber, if it was maybe a large open room. Or you might have something that is both a monster and a treasure if you're dealing with like a mimic in your D&D game. And those nodes can in addition to labels, can have attributes, which are just properties about that node. So in our room here, we have an ID and a name. And they can stand alone. Just like in a graph, these nodes don't have to have relationships. The relationships connect two nodes together. And they have a type, like contains or leads to. They have a direction. And they can also have attributes, although I tend not to use those a lot. Because nouns are more likely to have attributes than verbs, right? But the relationships tend to be verbs, transitive verbs specifically. And of important note is that the nodes can't, the relationships can't exist without a node. So if I delete, one of the nodes on this 20-sided die here, then there's no, there's nothing for them to connect to. The things that connect to them are gone because they are by definition 2 points, a line determined by 2 points. So if you delete a node, all of its relationships and associated data will go away. So I sort of hinted at this, but they read like a sentence. The room contains the monster, where a node is the subject and the direct object, and the relationship is a transitive verb connecting them together. So that's sort of a 6-minute or 7-minute quick rush through of graph theory and what the heck a graph database is. We've had enough theory. Let's solve our actual problem, right? We still got that problem of how to optimize our dungeon crawl experience. I still need to find that shortest path between the rooms, find the most treasure, find the most XP, that sort of stuff. And we still need to decide whether we're going to solve it with a relational database or a graph database. So if we're dealing with relational databases, in actual code, this is the language we use to talk to relational databases, SQL or SQL. You've probably used SQL and SQL to talk to relational databases before. There's a lot of them out there to choose from. I believe the first one I touched was Oracle back in the day. No, it wasn't. It was in college. Well, yeah, it doesn't matter. I don't remember the name of the first SQL relational database I used. It was just some little academic toy thing. But anyhow, we use SQL, and you're familiar with this. With the selects and the inserts and the updates and the joins and all that stuff. The comparable language for dealing with many graph databases is called Cypher. Cypher is a matching language. It kind of looks like a cross between ASCII art and a query language. And it was developed by the folks at Neo4j. And we actually use it at Redis Labs as well as part of Redis Graph. And this is the language we're going to explore in greater detail today. The key thing to understand about it initially is that it has this idea of matching. And so if you've used programming languages that have matching, this is a similar idea, where we have this ASCII artish kind of piece here where we have nodes represented by things in parentheses, which are kind of round and kind of like how my diagrams look. And then you've got, the labels are in here. So this little bit here is matching a room node. It's matching a node with a label of room and assigning it to the variable R. And this round thing over here matches a different node, which has a label of M, monster, and we assign it to an M. And then this matches a contains relationship. And it matches, you can see that little arrow there. That's showing the directionality that contains relationship. So it's actually kind of like we got two circles and a little arrow connecting them together in our ASCII, in our query. And this match then can be used to create nodes or in relationships or to go through the entire graph and find anything that matches that particular pattern, which is why they're called matchers. Getting started, I'm going to go through the Crud operations that you would use to talk to these things. We've got create, read, update, and delete, right? So we're going to create a room. We're going to read that room. We're going to update the room, and then we're going to delete the room. This is the SQL query that we'd use to create a room. Basic insert statement. This is how you would create a node and set properties on it in Cypher for graph. So here we're saying create, and then we got this little match here. And this is say create a node that matches this pattern. Create a node, give it the label of room, and then assign it to the variable R. And then set will allow us to set properties on that on that variable, on that node that we just created. What's interesting here is there's no schema. So in the relational database, we had a schema where we had to set the, up front, we said rooms have IDs and names. Here, we're saying rooms have whatever properties we want to give them. In our case, we have a convention where we're saying ID and name. But if we wanted to add another property, like say trapped, we could set that to a variable as well. So here we got create. And then once we create it, we get that node back that we've created and we can set properties on it. Now that we've created a node, let's go ahead and read it. So here, reading a room for SQL, we're using our the first thing you learn when you learn SQL is the select statement. Select ID name from rooms where ID equals 1. And if we look at the Cypher query for this, it's actually kind of similar. We're matching a room node. So we'll say match in the entire graph, look through the entire graph, and find everything that has a label of room, and assign that to the variable R. Then the where clause will filter that out. And there's actually, I believe, an optimization that happens here. So this doesn't grab everything and then filter. It actually does something smarter than that. But regardless, we're matching, we're filtering, and then we where the ID is the thing, and we return it. So match a node, filter out that list of nodes to just one, and then return that one thing. Or perhaps we have multiple rooms with the ID of 1. I guess it's not an ID if it's duplicated, but that syntax would return multiple things then. So we might be able to say match room where r.name equals a thing that rooms might have duplicate names. But this is a basic syntax, and this match where is worth paying attention to because it's going to recur here when it's time to update, right? So when we update a room, we use an update statement. We're taking our statue room and we're upgrading it to a statue hall. Shiny. To do that with Cypher, we're going to say match r::room. So this is that same match that we did before. Match that graph wherever we have a label of room, where filter that result. And then instead of returning R, this time we're going to set properties on R. And we can overwrite existing properties. So we're setting the name to a statue hall to change it from a room to a hall. But we could also add additional properties. Like we could add that trapped property I mentioned earlier in here. And that's updating. And then, of course, we can't forget everyone's favorite command, delete. Deletion, it's 100% file compression. To delete from SQL, you just say delete from rooms. Make sure you put that where clause in there. You're going to have a bad day. It's the same with Cypher. Here we're matching all the rooms. Make sure you put that where clause in there. You're going to have a bad day. And here is that match where again, but instead of setting properties on the thing that we matched, or instead of updating, or creating the thing that we matched, or returning the thing we matched. I'm sorry. We can delete the thing that we matched. So we can, return it, we can delete it, we can change it. But again, it's that match where, match where, match where. Worth noting is I'm using that match where syntax, but there is another syntax you can use, and this is what it gets optimized down to. You can say match a room. You can just do a match. And then in addition to saying a room, a label on a node, you can say, here are properties that I want you to match as well. And you put them in curly braces. And then you use basically a JavaScript object syntax to do this. It's not JavaScript under the covers. But it's the same sort of syntax where we have key value, key value, key value for the things that we want to match. And that will match all rooms that have an ID of 1. And there's no need to write the where. And this works on creation as well. Here we've done a create r::room, and then we set some properties. But we could have just as easily said, create a room node with these properties, and then that match creates a room that has these properties on it already. So these are just alternate syntaxes to do the same thing. And here's them in action here. So here I'm creating a monster, and you can see here I do :monster. I don't assign it to a variable because I don't need to refer to it. So there's no need to assign it to a variable. Doesn't hurt if you do. And then here you can even mix and match them. Here I've created a treasure, and I assign it to T and then set something on it as well. So you can kind of do a little bit of both. So let's take a look at our relational database so far. We've got 3 rooms with three tables with various rows. No relationships or anything between them yet. And our graph so far is just a bunch of nodes without any relationships. So just a bunch of points floating in space. So let's do something a little more interesting, right? Let's put a monster in a room. Because that's the thing we really care about. I need to have those monsters associated with the rooms. I need to have the treasure associated with the rooms if I want to query this for all the goodness that I want to find to optimize my character build. So to put a monster in a room using SQL, we have to modify the monster table and add a room ID column. This is the foreign key to the rooms. It says Alice the elf is in room 1 and Bob the ogre is in room 3. So we alter the table, adding that room, and then we update those rows in that table to put those monsters in a particular room. And so this is your basic one-to-many foreign key relationship that you use in SQL all the time. What does this look like in Cypher? Well, to put a monster in the room, you do matches and creates. So here we've got our first line of our Cypher query here is matching a room with an ID of 1, assigning that to the variable R, matching a monster with the ID of 4 and matching that to the variable M. Now we've got 2 nodes. Actually, we have 2 nodes in our graph here. And then we create a relationship using the create command between them. And so these R and M's here don't get created. They're already created. And this will just create a relationship between them, which will be created. And so this is how we put a monster in a room. We just create a relationship between them. To do the same thing for treasure, it's exactly the same, right? We alter the table, update the room ID for where the treasure's at. And in Cypher, it's exactly the same as well. We're matching on the room where the ID is 2 and the treasure where the ID is 6 here. And then we create a relationship between the room containing a treasure. So now our database is getting a little more interesting. Here we have a nice, very neat and tidy relational database where you have rooms with one-to-many relationships to monsters and treasures. And we have a graph that has some rooms that have relationships to those to things that they contain. So with this data, we can start doing some interesting queries. So let's be a little bit of a munchkin here and figure out how we can find the best monsters and the best gold. So if we want to farm all the XP, if we want to find the top level monsters that give us the most experience points for our adventure to level up with, we do what in our relational database, we would do a join where we're going to select from the rooms table and the monsters table and join them on the room ID. And then that will give us a list of every room and the monsters contained therein. And in this particular query, I'm selecting the ID of the room, the name of the room, and the XP of the monster because I don't really care about what their name is. I just care about the experience points because I'm a power gamer. And then we'll go ahead and order these by the experience points descending, and that will give me like a priority list of the biggest monsters to fight. Sounds great, right? How would we do this in Graph? Well, we can do matches on more than just nodes. We can do matches against relationships. And so this particular match here says, match in the graph, go through and find every room that contains a monster. If the room doesn't contain a monster, it's not going to come back. But match this pattern throughout the entire graph. And then of these, of this returned data, I want the ID, the name, and the experience points of those connected nodes. And then order by the experience points descending, in very much in the way we did with the relational database. But we can match more than nodes. We can match that whole pattern. We can match complex patterns, actually. Getting all the gold is going to be a similar thing, except we're going to join on the treasure table. And here we're going to do a relationship to the treasure table with the contains relationship. So cool, but not cool, right? So what, right? Yeah, I've used a more complicated thing to do the thing that I could do before, right? I haven't done anything with a graph database that I can't do with a relational database. So, well, this is where the interesting thing comes in, because when we start connecting rooms together. So in a graph database, this is really interesting because you can connect rooms in a very natural way, whereas in a relational database, you have to go through some machinations to make it happen. So let's take a look at these. So to connect rooms with a relational database, we need we have a many-to-many relationship from rooms to rooms, right? And to do that, we need some sort of table that maps them. So we need to create a table that's got all these connections of saying, the statue room has a hallway that leads back to the statue room, and the statue room has a hallway that leads to the barracks. And so we create that table that has that from ID and to ID to be that many-to-many mapping table for rooms. And then we can insert the connections we want into that. And you've probably done this pattern before, but it looks really different in Graph. In a Graph database, it's actually the same as putting monsters in the rooms because it's just another relationship. The leads to relationship and the nodes aren't particularly special. So here we can match a room, match another room, and just create a leads to relationship between them, just like putting the treasure in the room, just like putting the monster in the room. And so this makes for a relational database has actually gotten, even though this is a small problem, has gotten kind of gnarly. Whereas the Graph database, well, it kind of looks like what it is. It's a very clean representation. All the rooms are related in ways that are, I think it's more intuitive. My bias is that I think Graph databases are more intuitive. It's why I like them. So this is the part that I think is really different about Graph versus relational. So it's super munchkin time. Let's do some really interesting queries. And in order to do that, we need to do pathing queries. And you can do these pathing queries in SQL, but I don't have a lot of experience with them, and it's a newer language feature. But in Graph with Cypher, it's very natural. So here, what we can do is we can create matchers that match arbitrarily long paths in a graph. So this query right here, we're matching a room to a room, and that little star there means hop as many times as you need to. So this pattern would match in the graph a room connected to a room that leads to a room that leads to a room, room that leads to a room that leads to a room that leads to a room, et cetera, et cetera, et cetera, all the way out into the largest number that is necessary without creating circles in the graph. So the graph will figure out that it's doing something circular and stop. You won't get a Stack Overflow error or anything like that. And so this allows us to match more complex patterns. We can control that variable length relationship by giving it a minimum and maximum number of hops. So go at least one hop, but no more than 3. Right? So that could be useful. Now let's just do queries like finding nearby rooms. So here we want to match from room 1, which I'm in, give me all the rooms that are 1 or 2 hops away. So I have a choice of where I can go next. Kind of interesting. Let's make it a little more interesting. Let's find the nearby rooms that have the most gold. So I can get a list of, I can find the nearby room with the most gold. I can find the priority room to go to next. And so here, this is the same query as before. I'm starting in room 1, and I want rooms that are 1 or 2 hops away to another room. And that room has to contain a treasure. And so if that room doesn't contain a treasure, it doesn't match, and it won't be returned. And so this gives me a nice list of rooms, the room I'm in, the room I want to go to, and the treasure that's in it. And I can then return that and order it and limit it so that I get just the top room bubbling to the top there. I can also find the longest path through the dungeon. And I can do this because one of the things that you can do with these matchers is you can assign the paths that match to a variable in the same way that you can assign the rooms themselves and the nodes themselves and the connections themselves to variables. You can also assign the entire match. So this match p equals and then room leading to room star will find every path through the dungeon. This will match every single path in the dungeon. And it will assign that big list of paths to the variable p. And then I have functions that I can use in Cypher that will give me like the list of nodes that are in that path, or the length of that path, or the connections in that path. And so I get the list of nodes and the length, and then I assign it to a little variable here. And then I can order by that length and get the longest path. Cool. Normally you want to find the shortest path, but when you're in dungeon, you want to hit all the rooms, right? You can also use this to find this sort of stuff to find the room with the biggest treasure. So you can match something and do aggregation and assign it to a variable. So here we've got match all the treasure nodes, assigning to the little variable max, with a maximum aggregation against that gold piece value. So this matches all the treasure nodes in the graph, and then ultimately assigns to the variable max GP the value of the biggest treasure in the dungeon. Then we can match all the rooms that contain treasure where it has that gold piece value. And that gives us the room or rooms, if there's a tie, that have the biggest treasure. And we can use this to find perhaps the monster query of them all, the path to the most gold. So assuming I start in room 1, I want to find the room that has the most gold and then get the path to it, the shortest path there. So here we're going to match our treasure, just like we did earlier. Find the biggest treasure in the dungeon, find the room that contains that treasure, and assign that to the variable dest ID. So this finds the room that we want to go to. Then we can match the path like we did earlier from the start room to the stop room. And the stop room is the room that we found in our previous match. So we've got 3 matches in this query so far. Then I can return the nodes and the lengths of those, order it by length ascending, which means the shortest path would be first, and then limit it to 1. And that will give me the shortest path to the biggest treasure in the dungeon. So I think that's pretty much it. I'm going to skip my demo because I'm a little short on time here. But practical applications, obviously, we're not going to use this for Dungeons & Dragons. Oh, maybe you will. I hope you do. It's fun. But you can use it for social networks, genealogy, transportation networks, logistics. These are all things that are natural graph applications. So if you can do these for serious things too, not just for fun, ridiculous things like I do. Here's a list of resources to check out. The key ones here are, if you want to play with Redis Graph, is redisgraph.io. And we have here's a Cypher query language reference and OpenCypher here from Neo4j. OpenCypher is worth checking out as well for the full language reference. I work for Redis, and so we got some resources I'd like you to check out. Probably the one I want you to check out the most is our Discord server. That's where I hang out all the time. So if you have any questions, you can ask me there. And yeah, that's pretty much what I got. Here's a QR code that totally doesn't rickroll you and totally takes you to the repo for this. And yeah, thanks a lot. My name's Guy Royse. I'm with Redis Labs. Thanks for watching my talk.